Okay, since we live in a 3D world, we got to talk about vectors in space. We got to add in that third dimension. So we've looked at them in the XY plane before, and we've done dot products, we've done position vectors, we've done angle between them. Today, all we're really looking at is bringing that out to a K, so a third dimension here. All the rules, all our formulas are pretty much going to follow the same thing. There's just one extra step in them, just dealing with this guy here. Okay, so not a ton new here today. You're making a 3D axis. So the way you can think about it is the XY plane that we used to graph flat, okay, becomes like the floor of a classroom or something. Okay, so the XY plane's like what you guys would sit on. The Z-axis comes right off of this. Okay, that could be like the corner of the wall. So if we wanted to take my classroom, we wanted to plot a point in it. Okay, we can't describe it with just 2 dimensions, we could describe it with 3. I'll show you guys in class how we make a grid with our hands, but basically you're going to point your index finger at X, you're going to flick off Y with your middle finger to make a 90-degree angle with those, and then you're going to go thumbs up to Z. All right. Now, if I got some vector in space, let's say comes out this way, I should be able to do a lot of different things with it. Okay, first thing I should be able to do is find distance. Well, just kind of makes sense. It's going to be the same distance formula as before. So 2-dimensional distance formula is this, x2 minus x1 squared, y2 minus y1. It's just Pythagorean theorem, distance formula in 2 dimensions. It's the same idea, we just add another one in here in the 3rd dimension, and we square root all this stuff. So you guys can get a visual idea of what's really happening with this. Let's look at this. So here's the Geometry Sketchpad. Here's the x-axis, here's the y-axis. Now I know they're backwards from what you guys are used to, but we could easily go, over 4, up 4 on the y. Okay, you guys know how to graph in 2Ds. What happens when we go 3 dimensions is we drop this x-axis flat, and we put in a z-axis up there. So we're pointing at x, we're flicking off y, and there's the z. So if I want to plot 4, -3, -2, I'm going positive 4 in the x, I'm going -3 in the y, and -2 in the z. So basically, I just made a line from the origin for all of these things. Positive 4x, -2z, -3y. And if you make right angles at all of these, okay, new 90-degree intersections with the 3 things, you'll get the point you desire, which is the red guy down here for us. Okay, we went up 4, we went back 3 for the y, and we went down 2 for the z. So you're always staying on the axis, or you're always staying parallel to them. So let's change this up so you can see a different one. Let's go -5 in the x. Let's go positive 7y. And let's make this z, let's go positive 4. So that first time we were graphing it in 2 dimensions. If we bring this guy back up again. Now if we move this back to the origin and we graph it with the 3 axes right now, you can see how this thing's moving. In an x and a y and a z, and there's the point that we want. So -5x took us back to here. Okay, we can even do it out of order if you want. The 4z is going to take us straight up here, and 7y is going to take us over to here. You can create your 3-dimensional box with all the lines. Okay? So you can imagine we could put a line in from here out to that point, and we could find the distance of it. So basically, it's a 3-dimensional Pythagorean theorem to find that distance there. All right, what else can we do? Well, we've done position vectors in 2 dimensions. That means we're basically just Resetting it here back to the origin. So if I pick 2 points on here, I'm kind of finding the length of it, x2 minus x1, y2 minus y1, and so on, and I'm just resetting this back to the origin, okay? These are actually backwards. I'm not sure how that happened. The book screwed these guys up. But position vectors, we always want to be the second minus the first one. So it's the book's typing there. So yeah, so it's going to be our basic position vector. We're just adding in a z component now too, with the k's. We're subtracting y's, subtracting x's, subtracting z's. All right. So here's kind of a three-dimensional scale here. Here's some vector out here. It's an a, b, and a c. Here's how you want to find the position vector. So this guy's written correctly. So that's good there. Like we said, you just want to subtract these, and there's one addition to your formula. So if you know position vector for 3 dimensions, you can easily do it for 2 dimensions, just chopping this guy out. Okay, so let's say I give you 2 vectors here. So you could play around with the Sketchpad file, and we could actually plot each of those points, or you could kind of think about where they are. We want to find the distance. We want to find the position vector. I'm going to pause it here to save some time and see if you guys plug in and get the same numbers as. So here's all the work for it. Distance should be square root of 13. Here's our position vector. If we took these 2 guys and basically found the vector between them and reset it to the origin. Now notice you're doing the same calculations finding distance as you are position vector. All we did for distance was after we subtracted them, we squared them. So this squared plus this squared plus this squared, and then we square rooted it. Okay? So the vector, you really only have to do once. So you can see I showed all the work here just so you don't mess up anything with positives, negatives. Take this guy, find the distance of it. You're basically just finding the magnitude type thing. Okay, so those 2 questions are really related. Like I said, a lot of the same rules are going to happen as we did before. So now I got 2 vectors that are in space. So they got a k component and another k component. We add them the same way. All we do is we add on this guy. We subtract them the same way. All we do is we add on this k component here. Okay, a minus a, b minus b, c minus c. We multiply them by a scalar the same way. If I had a v and I wanted to do 5v, I'm going to multiply all 3 components by 5, and I find the magnitude of each individual vector the same way I did before. All I did is add in a c. Okay, so before we go over to part 2 here, I want you guys to think about how we would do unit vectors in the same direction, how we would do a dot product, and how we would find the angle between 2 vectors if they're in space now instead of on a plane. Okay, think about those, and I'll see you guys over in part 2.